ending then. So to get started, I'll share my screen here real quick. Let me know if you can see my presentation, the first slide.
Yes, we see it.
Awesome. So as was already stated, this is a story about extremes, as so many stories in planetary geology are. I will offer you a glimpse, of course. This is a specific study about a specific area on Mars, but it can serve as a template, a deep insight into also other regions on Mars, and to understand the planet itself and how we as planetary scientists approach these questions, these big questions about how planets, including Earth, evolved. And also why, for example, we pick an area to study in the first place. So let's get started. I'll offer you a real brief crash course on Mars. So why do we study Mars? It's smaller, it has less gravity, it has a thinner atmosphere, it's colder than Earth. But if you look at the geologic timescale on the bottom, it offers information that is largely lost on Earth. Most of the planets offer information that is mostly lost on Earth in terms of timescales, because Earth has such a young surface that rejuvenates itself all the time due to weathering and plate tectonics, phenomenon that are not or much less existent on almost all other planetary bodies in the solar system. On Mars, however, other than, for example, the moon, we see a lot of the processes that took place on Earth and are still taking place on Earth, evidence for those processes in Mars past. So we can really study how these behaved over timescales that we cannot access anymore for the most part on Earth. And of course, all this comes back to better understanding Earth and any planet. So that's why you should never call someone a Mars scientist, call them a planetary scientist. It's always about all of it. So, I would like to draw a full circle here to these people, for example, just as an example. You might recognize a few of those, of course, the great Carl Sagan, a fellow astronomer. There's Bruce Murray, Lewis Friedman, people who founded the Planetary Society, and who were probably the first, or at least some of the most pivotal figures that were faced with, the next slide, the Mars dilemma. So what is the Mars dilemma? It started in those grand olden times that I just referenced with these researchers that are not among us anymore, already with data from the Viking orbiters and even previous missions, the Mariner missions, where we saw large valley networks and evidence for activity of liquids, probably liquid water, on the surface of Mars. And we saw large, huge volcanoes, the largest ones in the solar system. So does that indicate Mars in its past was warm and wet? Now, more recent modeling and detailed mapping on high resolution, on a global scale, showed us that, yes, indeed, warm and wet early Mars is possible and indicated by a lot of not just big, but also small valleys. That formed around 3.8 to 3.6 billion years ago. Billion, not million, billion years ago. So this is older than the oldest rocks you find on the bottom of Grand Canyon. So this already tells you, like, all of this stuff is so much older than most of the stuff we know on Earth. But 3.6 billion years, that's a youngster for any moon or Mars rock, for example. Now, the dilemma arises when climate modeling enters the stage, and sophisticated climate modeling that shows us that with Mars being further away from the sun, and as some of you might know, the sun having been weaker in the distant past, you cannot warm up Mars enough to get all the liquid water to form all these river valleys. So, so what happens? Like you have a cold and icy Mars, early Mars implied by the models, but large and small scale observations indicate a warm, wet Mars. So this is the Mars dilemma, something that a lot of scientists have been, a lot of planetary scientists have been chewing on over the past, let's say 15 years at least. And sort of the image that emerges is one of the puzzle pieces of that image is, for example, the study I'm going to present here now. So how to get a cold and icy environment warm. So of course, we have a lot of more exotic approaches, like it might have been methane bursts that created really warm but very short-lived conditions coming out of the subsurface, or the water might have been rich in anti-freeze solutions like exotic salts that kept it from freezing even at 20 centigrade below zero. Those are solutions that only offer very small scale scenarios. We're looking at a bigger picture. We need something that happens over and over and over all over the planet. Now, large impacts, as you probably know, asteroid impacts change the environment, change the climate, causing extinctions on Earth, for example, also causing climate changes on other planets like Mars. So that would be a suitable candidate. And there's also volcanic induction, as we've seen in the past, the recent past. Volcanic eruptions can create climatic effects, as well as global large-scale climate changing effects as well. And this is something we're going to talk about more here now. They deposit ash that make the surface darker, lowering the albedo, and that increases surface temperature due to higher infrared absorption, as well as all the aerosols and the outgassing of species like hydrogen, which is one of the most potent greenhouse gases ever. No one thinks about hydrogen. It's not important for climate change on Earth in the long term because it decays quickly, but even quicker than, or it gets lost to space, even quicker than methane. But forget about CO2. Hydrogen, and to a lesser degree methane, are the stars of the show when it comes to global warming, at least in the short term. And those bursts is what we possibly are looking at. So now, this is all a nice story, but where's the evidence for that? What geologic observations can we make that support these proposals? On Earth, we know that this exists and has influenced history, the history of life, the geologic history of Earth tremendously. Volcano ice interactions can set free large amounts of not just liquid water, but all sorts of gases, including steam, of course, steam being a very potent greenhouse gas. And the ash clouds that, due to the internal friction and the separation of charges, they can create lightning. Now, if you remember your biology classes, the emergence of life is theorized to have taken place in an environment where organic rich solutions are subject to electric discharge. And exactly these environments are created around volcanic eruptions that interact with large bodies of water ice on and around them. As I said, we see that on Earth today. We see evidence of that on Earth in the past. Now, what about Mars then? Malia Planum is the area that I'm going to talk about today. It's the area that you can see on this wonderful HRC image. That's a camera on board of the European Mars Express probe that takes pictures in color. It sits right between this biggest hole on Mars that is called Hellas Planitia. This is where I focused my PhD studies on that were mentioned earlier. And on the other end, it's framed by the south polar cap of Mars. So two very prominent features on Mars that frame this area called Malia Planum. It is the most heavily cratered, and therefore likely oldest, of the large volcanic provinces of Mars. Now, many of you might know Olympus Mons, the Tharsis province. That's probably the most popular, most well-known volcanic province on Mars, with the biggest volcano in the solar system that stands over 24 kilometers high. This area is topographically much less remarkable. Nevertheless, it is interesting because it's so heavily cratered. It is old, so it can tell us something about the very early large-scale volcanic activity on Mars. So just as a brief interjection, the more craters the surface has, the older we, at least at first scale, interpret it to be. It's like with a person, the more wrinkles a person has, the older we think a person is, or the more that person hangs out in the sun. The thing is that there's a lot of considerations that go into that, but at first glance we can say heavily cratered means old. So also the adjacent areas that I also already mentioned, Hellas Planitia and the South Pole, they are very important because they frame Malia Planum and Hellas Planitia, a big hole. A big hole is always a collector for stuff like your kitchen sink. And so there is a stratigraphic record, sediments in there. And now it's important to understand where all these sediments came from. Well, they came from adjacent areas that when that stuff got washed or blown into the basin, but how, when, and how much, from where exactly? And then the South Pole, well, there's a lot of ice there, dry ice, but also water ice. Now we have a big volcanic area sitting right next to the South Pole. So what exactly are the interactions between these two areas? To move on, this is a topographic view of the area. You can see there are big holes here we call patera. That is just a term that is attempting to not be too interpretative. So in planetary science, we try to use neutral terms for the sake of not overinterpreting things. So is it a volcano? Is it an impact crater? Is it something else? In general, the term patera just means it's a roundish depression that is probably not an impact crater, might be something else. So there are different paterae all around Mars. These four that you see here, Pityusa, Malea, Peneus, and Amphitrite, are the largest ones on the entire planet. So those names all derived themselves from terms from Greek geography. So because we are sitting south of Hellas basin, Hellas being the Greek word for Greece. Now, the other holes that you see here, those are probably impact craters. This one is called Bernhardt. This one is called Mitchell. That's just the two biggest ones. There are other named craters in the area as well. Also big valleys, big channelized areas, a lot of channels that follow the topographic gradient down from the brownish red areas through the yellow areas down to the green and blue. Like blue is all low. That's where the big basin Hellas Planitia is. And you can see the elevation difference. We're talking about 6 kilometers from here to here. So that's quite a difference. That's the difference between Mount Whitney and the coast. And those are quite drastic topographic variations here. So I'm going to throw this at you just as a bit of an eye candy. You don't have to read anything on this. It's very small on purpose. This is just to showcase what an end product looks like if we map an area to understand it, to make an inventory of all the geologic landforms that we can see in an area. So we synthesize all the knowledge we have. Of course, we cast an interpretation onto the landscape by mapping something as, for example, here, let's take the very first unit, dark dunes. Now, of course, a dune already is an interpretation. A dune is a specific type of feature and all these things. Now, we make observations from the orbital images, and then we compare them with features on Earth that we can access in the field, for example, to better understand them. And then we cast these interpretations onto other planets and therefore inform our inventory that we put in a two-dimensional format, and that essentially is a map. Now, a geologic map or geomorphic map or morphologic map, all these things are not exactly the same, which is something I'm going to touch on again. A geomorphic map is sort of a Frankenstein monster between a geologic map and a morphologic map. You can buy a geologic map of Arizona and you can buy a morphologic map of Arizona. There will be similarities, but in essence, they're different. In this case, I show an area in the Arctic that I worked at on the Svalbard Archipelago. This is a geologic, and this is a morphologic map. This is just to show you one specific method with which a planetary scientist can approach a planetary surface. Now, of course, there are colleagues who assess an area and don't include necessarily a map because they're focused on a specific feature. If, as I did, a holistic approach that takes into account the entire history and inventory of an entire area is desired, a map is the go-to approach because then, well, a map covers everything unless it has holes, of course. Nevertheless, the information, so it's always a data reduction. I mean, you can have a very fancy map. Why not show a photo of the area? Because a map codifies information in colors and symbology, and that information for a geologic map might be the lithology. That means what kind of rock? Is it a granite? Is it a basalt? Is it a sandstone or a limestone? Tectonic line work, like what tectonic features, structures do we see? Is there a normal fault? Is there a thrust fault? And so forth. And of course, stratigraphic relations. Do the dunes sit on top of a basalt layer? Does the sandstone sit on top of limestone the other way around? And so forth. Now, a morphologic map doesn't care for stratigraphy necessarily. That is, when things happened, in what kind of sequence they are deposited on the surface. It just cares about describing the shape of the surface. Is this a gravelly debris fan? Is this a smooth pediment? And so forth. Now, a lot of the information contained in a geologic map is not accessible at present from orbital data on Mars. Now, we have a few landers on Mars, but those are very punctuated, localized pieces of information. And there's no lander anywhere close, for example, to the area that I showed you. So we're limited to orbital information, and you can create geologic maps from orbital images alone. People do that on Earth as well. They're so lazy, they don't even go in the field anymore. Nevertheless, you need to verify, at least in some areas. Now, we cannot do that. So it is a Frankenstein monster between a morphologic and a geologic map. This is just a little short deep dive into one specific methodology of planetary science. Now, going back to our geomorphologic map, where we have geologic and morphologic unit that are coupled with certain interpretations. Nevertheless, it is kept as neutral as possible. A map should never be too interpretative. Otherwise, it doesn't get very old because, as you might know in science, interpretations and ideas change. You want your map to last and be usable by the next generation, ideally. So this is just eye candy. You can see there is purple stuff, there is brownish, ochreish stuff, there's yellowish stuff, and so forth. But you see that there's different units and all the yellowish and ochreish stuff that's ejecta and placed by craters. And then there's other stuff that is not related to impact craters and so forth. This is just supposed to be in an eye chart, so to speak. Now, there are different kinds of units. The purplish stuff is probably primarily volcanic. Now, I will not go into too much detail on why that is and all these things. I will just mention several aspects. But just to show, we can differentiate the units according to how we interpret they formed. So these are the units that we interpret are primarily of volcanic origin. There are several observations that we can make. And so, as I said, we try to be very non-interpretative when we describe the units at first. So they always have these very unspectacular names like ridge plains, duh. So, well, there are plains that have ridges. All right. The N, the large N here, is the capital N always is one of the three geologic periods that we differentiate among in the Martian stratigraphy. This is the oldest one, Noachian, it's derived from Noah, the biblical figure. Then there is the second period is called Hesperian. And the third one is the Amazonian. Those are named after areas on Mars that serve as the type region. The same thing for Earth. For example, the Cambrian, when multicellular life really became widespread on Earth, that is named after the type area, specific small region in England. So we do the same thing on Mars, albeit we have much larger timescales because we don't know as much yet. We see that there are these round arrangements of ridges which are buried craters. So this is a crater that sits just beneath the surface and its rim just peeks through and causes the overlying material to be a little bit upward. And so we know there's something that got deposited here. And we know that there used to be craters before that were then filled up by something that created a very smooth and even surface. So it must have been something that's very runny and filled all nooks and crannies everywhere and just filled it up to a homogeneous level. So it must have been very, not something that was too viscous, not something that was brought in by wind, because then it would not be as homogeneous. So it must have been something that probably flowed across the surface. So this might have been something related to water, something related to lava. And there are several aspects that make us think that it's probably volcanic lava and not sediment, as in like laid down by water, for example. Now, we can look at these ridges and analyze them, and with structural modeling, things that we also know from Earth, how thrust faults and these kind of ridges form and look like. We can derive how thick that stuff must be, especially in a case like this, because we know how deep a crater should be, depending on its diameter. There's a certain ratio, an empiric factor that you can derive. If you look at all the craters in the area and see how deep they are in relation to their diameter, now we see the diameter here, and then we know how deep it is and how much stuff must be in there that filled it up. And then we know how thick this unit is. And then we see its areal extent because we mapped it. And we can make a first estimate of how much stuff there is. So an areal extends square kilometers times the thickness in kilometers. And we have kilometers to the power of 3. We have a volume. And in this case, we're talking about 1 million cubic kilometers. That is a lot of stuff. If you ever heard, for example, one of the biggest volcanic units on Earth that might have been also responsible for the extinction of the dinosaurs, large volcanic eruption, the Deccan Traps, that's less than that. That Deccan Traps are smaller than this volume. So this is 2.5 times the Deccan Traps, for example. We're talking about a very, very large volcanic deposit here. I mentioned those big holes, the paterae. So let's compare them with other holes that were formed by volcanoes, calderas, we call them on Earth. You all know the Yellowstone caldera probably, I hope you do. That's that large. That's a large one already. Then the largest caldera on Earth, that's a submarine caldera in the Philippine Sea, is this large. Then there is a similar looking feature, which is probably also volcanic caldera on Venus, that is this large. And then there's this guy we're looking at here in the study area. And then there's a similar one also on Mars that might be then the biggest one on Mars, where it's basically the same size. So there was discussion, is this too large for a caldera? Well, based on the largest caldera on Earth, it's about 0.5 times larger than that. So it's not out of the question. It's not ridiculously oversized. It is huge, but it's still comparable in size to the biggest caldera on Earth that we know is a volcanic caldera. So size-wise, this would be in agreement with an interpretation as a volcanic caldera. This is a close-up of the area. It's all mottled and degraded, as you see. There's stuff inside. It's not fresh. As I said, these features are billions of years old, billions of years of wind and probably this fluvial activity, glacial activity, later volcanic activity, and so forth. Nevertheless, it's still there because it is very, very large. This is a close-up of this mountain you see that sits inside of the big hole, the big patera. And you see those weird lines on it, those curvy linear lines. Now, these are layers, deformed layers. Like in mountain ranges, when you squish everything together, the layers, the sedimentary layers, volcanic stuff can also form layers, get all jumbled up. If you've been to the Superstition Mountains, you know what I'm talking about. Now we can measure how these layers are oriented. Even from orbit, we can do that because we have high resolution topographic data. And then you can do that from orbit. So the dip of those layers is on average 12 degrees. And we measured a lot of those so-called batting attitudes. And here, there's a map of just a part of it. And there's even areas where you see ups and downs, real wave patterns where stuff just got squished together. And we can derive how much of contraction happens to squish it together that much. And it's about 2%. So how might that have formed? How do we get contraction in this area? Now we know that in calderas on Earth, contraction can happen in the same way. Compression can happen in the same way. I'm going to move on. This is a stratigraphic model of the area, how we think it looks like. Now, this is the measured topography surface. That is truth. Everything below that in color is an interpretation. Now we see these spikes, though that's height exaggerated, but those spikes are the mountain peaks of that compressed material. And imagine you have a funnel that you push cream through in order to ice a cake. So that stuff gets compressed as you press it down into the through the funnel. Now, if a volcanic caldera forms, a volcanic caldera, just like Yellowstone, forms because stuff beneath disappears, because it erupts. The magma chamber gets emptied, and then everything will, on top of it, sags down. And it can sag down in a way, in an almost V-shaped funnel type way. And then, of course, everything in that down sagging plug can get compressed. And you have an area where shortening occurs, compression. And that could explain those lines. And that kind of compression would perfectly explain the measurements we made earlier of 2% shortening. So you would arrive to would be 0.5 to 3.4. So that falls perfectly around our 2%. So the model interpretation fits to the observation. And that's as close as you ever get to an evidence based on orbital data. Now there's other things we can derive. I'm not going to go too much into detail here. Other very smart people. The bottom line is that we can also derive based on the size of this and its depth, how deep that magma chamber might have been. And it might have been very deep, this deep. Yellowstone, for example, is only a few kilometers. Mount St. Helens, the magma chamber, is just a kilometer. And here we're talking about maybe 17 kilometers. Now there are volcanoes on Earth where that also occurs, but that is very deep. That's almost in the mantle, exactly at the interface between the crust and the mantle. Very, very interesting, but not too surprising if you look at the dimensions here. This is another aspect of something I mentioned before. This is now that tectonic mapping. And that shows you how the tectonic features relate to those big paterae. Here, two examples, one from Earth, one from Venus, where we also have magma chambers beneath calderas that are so deep. By the way, the word caldera is Latin for cauldron, because it's a bowl-shaped depression. It's not always bowl-shaped. It can be elongated. It can even be angular. It can be very round. Nevertheless, that's where the name caldera comes from. And patera on Mars is used because we don't yet want to call it caldera. We want to be non-interpretative. We want to be neutral. Nevertheless, these patera are most likely volcanic calderas. And just like, for example, Medicine Lake, that's in the Cascades, highly recommended, very interesting area to visit that. That's where stuff comes up from the mantle. So it's not like Mount St. Helens, for example, where the erupting material originates from relatively shallow depths within the crust. No, it's stuff that is derived directly all the way from the mantle. That makes, of course, very interesting because it's not every day that you get stuff from that deep. And the question is why? Why does stuff come up from that deep? You have to go through all the way through the crust. What makes it come up? How? So here we sit next to that big impact basin called Hellas. And remember that big hole, right? So such big impact basins fracture the crust all the way through. That happened on Earth when big impact basins formed, none of which exist anymore. Stupid plate tectonics. But that's the case on the Moon, on Mercury, on Mars. And lo and behold, if you look on the fringes of those big impact basins on Mercury, Moon, and Mars, volcanoes tend to be there. Where do volcanoes tend to be on Earth? They tend to be along plate boundaries, the Cascades, because the plate boundaries act in a similar way. That's where the crust is broken. And here the crust is broken not by because it's a plate boundary or because plate tectonics occurs, but because that big impact fractured it along its fringes. And that allows material to come up from beneath because there's a pathway. And then also mantle flows get disturbed by those big impacts, just as well as they get disturbed at plate boundaries. So all these things coming together can enable volcanism that comes up from that deep. Now, there are a few more observations that we can make from orbit that have not been successful so far. We can look at that material with those wavy lines that got squished together, because those might be deposits from those volcanic explosions that formed the patera. And that might be stuff from the mantle then, that got derived from the mantle. Now, we would expect certain minerals to be in there. For example, magnesium-rich olivine, that's something that we think should be coming from the mantle. We haven't seen that yet because it's so dusty. As you know, Mars is dusty and it messes a lot with spectral observations. But keep your fingers crossed, maybe in the next few years, we will catch a good moment and see a dust-free patch on that area and see that, or not. That would also be interesting to not see that. Anyways, now the second part, so this was the fire part. Now, where's the ice part? Okay, so we see a lot of channels and we see a lot of other units here that are not volcanic, but they are associated with a lot of channels or ridges, curvilinear ridges. So they are possibly formed by flow processes, and those appear to be not volcanic, but fluvial, by water on the surface, or glaciofluvial, water that is derived not from rainfall or groundwater sapping, but meltwater from glaciers. And that might also be beneath a glacier or in front of a glacier. And you see there's a lot of that. There's a lot of them, and very disconnected in places because the surface is old and it gets degraded. But here there are a lot of intact ones, and this goes all down into the Hellas Basin. So it's important because now we find out where all the stuff that sits in the biggest hole of Mars comes from. So there's a close-up of the area. PP and AP is the Peneus Patera, Amphitrite Patera, one of those two big patera that are most likely volcanic calderas I mentioned before. And all these channels going down, all these channels. There's Bernhardt crater, that's an impact crater. It has little curvilinear ridges inside that might be of glacial origin. And there is a very big valley called Mad Vallis, not Mad, it's Mad Vallis. And that empties, or it follows the topographic gradient going down in the Hellas Basin as well. This should be full screen. It's unfortunately not. I have to live with it. Anyways, this is one of those big volcanoes, the Amphitrite Patera, and down its flanks go all these small channels. Now you might say, hey, there's channels going down a volcano, so it's probably lava, right? Possibly, maybe. Let's compare a little bit. This is what we just looked at. See, it's very degraded, but there's confluences, diffluences, and they are just sinuous. And this is an ash flow down a volcano in Chile, one of the biggest ones on Earth. This is Kamchatka. These are fluvial channels down a volcano created by melting ice on a volcano. This is a big lava channel in which now a small glacier resides. It reused the lava channel like a crab reusing a shell. And this is on Tenerife, Teide, lovely volcano. And these are actual lava channels made out of lava. So you would see a similar thing on Iceland, very fresh. So now we have to decide, we have to differentiate which commonalities we see. So, and to cut a long story short, the only other example of this interfering, the diffluences and confluences, that braided pattern, the high sinuosity, we see in actual lava channels. Now, there's something weird about this though, because they are so long. And the slope of that volcano, the video I just showed you, the height was exaggerated. So actually the slope is extremely shallow. If you stand there, you wouldn't notice you're standing on a slope. That's how shallow the slope is. Now, and these channels run over hundreds of kilometers. Lava doesn't do that, at least not lava we know. It will get stuck way too early. The channels the lava flowed down in on Iceland, recent eruptions, many of you hopefully saw on YouTube, are very, very steep, and the lava flows maybe a few hundred meters, maybe a few kilometers, and then it's dead. So how can it flow hundreds of kilometers on a slope that is so gentle that you would barely notice it? So it must be very runny and much thinner than any lava we know. So either we're talking about a low viscosity lava that is exotic, nothing that we see today on Earth at least, or we're talking about water or very dirty water up to mud that formed these channels. All the other observations, the sinuosity, size, and branching, as in the width and depth size, then the inner branching that's coming, diffluences and confluence come back together. The levees are these small walls lining along the channels. They're called levees. The density of those channels in general, none of that is diagnostic. All of these things can be formed by lava and water. So this is another close-up here. This is just looking at the width of this channel here as it broke through. This is the rim of that patera, and the channel broke through here. So it started within the patera at a time where the patera already existed. So it's probably not related to the formation of the patera, of that potential volcanic caldera itself. So climate models also suggest that this would be an area where a glacier would form if you make the Martian atmosphere just a little bit thicker, excuse me. And in the past, it was thicker, we know that. So these could have been meltwater channels. Anyhow, if we look at the width of this channel, it's very wide, and calculate how much lava you would need to carve this channel out, to fill it, and to create a gap that wide. In this instance here, for example, we can derive how much lava must have went down this channel and all the other ones. And we end up with a volume of lava per second flow rate that is comparable to very, very, very large eruptions on Earth. So again, same with the size argument with the other patera calderas in the first place. There would be very large ones, but it's not out of the question. And the same is here, the case. So not unreasonable, but certainly extraordinary. So other channels that we see cannot have been formed by lava. They must have been formed by water. For example, here, where you can see actual cutoffs of meanders, like in a river, with oxbow lakes being created. And that is something that is very, very difficult, probably impossible to achieve with lava. So, and this is on the other end of the area, for example. So lava might have been involved to form some of these channels, and quite likely even the interaction between volcanic heat and glaciers, and then the resulting meltwater or mud avalanches as well. But there are some areas where we know that the channels cannot have been formed by lava, must have been formed by water. Lava might have then reoccupied the channels. That happened in Iceland recently. A few months ago, we saw that. That sneaky lava went down the hill in a pre-existing dry river. Happens. Nevertheless, some of those channels must have been originally formed by water on the surface. Now, this is the biggest one, the Maadvallis I mentioned, that connects the South Pole, which sits right here, with the Hellas Basin. So we were able to trace it all the way to the South Pole. So we have a continuous conveyor belt of stuff, sediments, that flowed from the South Pole across this area, Malia Planum, all the way into the biggest hole of Mars. So a very large area of connected sediment transport. So, and due to previous studies, we know that 1 million cubic kilometers of stuff once was in the Hellas Basin. So, and a lot of that might have come from this area and even the South Pole area. And the volcanism in this area might have made this transport possible because it liquefied, it mobilized a lot of material. And approaching a close, so now I told you a lot about different processes, but now we want to know when did what happen? Right now, it's just a jumble of different things that happened here and there. So what's the story? Now, in order to figure that out, we can look at stratigraphy, as I mentioned earlier, like one thing over the other, and then we know which one has to be older. But this area is very difficult for that. In some cases, we do see good stratigraphy. In many cases, we do not, because Mars, as I said, is dusty, and the dust covers everything, and this is a specifically dusty area. Even with a cemented dust, we call it dust ice mantle, that sits on top of everything and covers up your precious stratigraphy in many places. Another thing we can do is counting craters. I mentioned earlier, the more craters, the older. Now, this is just to showcase where we counted craters. You can't count craters everywhere. You have to be very careful which area to choose. It's like counting tree rings in order to determine the age of a tree, or carbon-carbon dating that is used in archaeology to determine when a tree was chopped down and when a certain structure that used the wood was built. You compare two different carbon isotopes, their relative amounts. You look at the amount of tree rings, and here we look at the amount of craters. Crater formation is a random process, more or less. So we may assume that the more craters the surface has, the older it is. And there is also a difference between how many smaller and larger craters and so forth. Safe to say, we counted a bunch of those craters. Each of those images is a distribution of craters in each of those areas. And then you associate that age with the geological unit that those craters are in. And we couldn't do any of this without the Apollo missions. Now, Apollo was Moon, but this is Mars. Well, it all hinges on that because we got the samples from the Moon. And then we transposed that knowledge to Mars. Yes, it is a transposition. It is an extrapolation, but it's the best method we have right now to determine absolute ages of surfaces in the solar system. So now is the story. So this is a stratigraphic chart. Each of those colorful ribbons is one of our units. Here's that purple unit, the ridged plains, which we think is a volcanic. Here's one of the glacial units. The blue one, of course, is one of the probable fluvial units. And we have them stacked up in this way because this is what we see based on stratigraphy, as well as those model ages. Now, model ages, we like to call them, those are the ages that come from the crater counting. We always call them model ages to remind everybody that those are model ages. There are best guesses in terms of absolute age based on our current knowledge of crater formation and so forth. And they will definitely be improved on in the future when we get samples back from Mars and can date those samples actually. We have samples from Mars in the form of meteorites, but we don't know where exactly on Mars they come from. We need to know where exactly a sample comes from to see how cratered that surface is, and then we can date the sample and know how old it is, and then we have a laboratory age with a crater density it came from, and then we know how many craters correspond to what age. And on the Moon, we do that. We have Apollo samples, and we transpose that over to Mars, and that's our best guess right now with the model ages. Nevertheless, they correspond well to the stratigraphy we see reasonably well. So those red bars are the model ages, and then the actual placement within this stratigraphic story here is within those bars. It touches those bars in every place. So that's sort of a sanity check. And those are the different crater sizes and the statistics that go into the crater dating method. And then we compare that with other literature that worked in the area or adjacent areas before. And we can derive a story of our area. So we start with that large hole, one of the four large holes, one of the four patera, Pityusa patera. That's the one with the folded mountains inside that I told you more about earlier. And an adjacent one called Malia patera. Now, but here Malia patera, I drew that as a mountain. Why? That's pre-collapse. Mount St. Helens or San Francisco Peaks. After an eruption occurs and part of volcano collapses, it forms a caldera, and it might not have, or even better example, Crater Lake. I hope everybody's been to Crater Lake, and now again, highly recommend it. That used to be a very, very, very tall mountain. And now it's just a big hole with a lake inside. That is how a caldera forms. It's a collapse. And in the end, you're left with a hole, which used to be a mountain. And in most cases, used to be a mountain. And so in this artist interpretation, with my extraordinary artistic skills, I propose it to have looked like this, just because of the sheer amounts of material that must have erupted from this area. It's hard to think that there was not a mountain of stuff that had built up around the vent originally. And this low viscosity lava that comes out from it then gently covers the entire area. We know low viscosity, very runny lavas were more common in Earth's distant past, and it's reasonable to assume that those lavas were very common on Mars' distant past as well. Imagine stuff that is as liquid as warm maple syrup. So very, very liquid. It can run down even a shallow slope. Compare that to Hawaiian lavas nowadays, which is between toothpaste and ketchup. This is warm maple syrup, covering everything, including the craters. And then you get those ring structures I showed you earlier, ring-formed ridges, where the crater was just about buried. Now moving on, now comes, so this was the fire bed, now comes the ice bed again, right? So we have continuing eruptions, the other two patera, so there are four, the first two already erupted, now come the other two. And then there's also glaciers forming around them. That we know because of climate models that indicate a glacier should be forming there due to winds and elevation and all that if you make the air just a little bit thicker. And it was, we know that. So there probably was a glacier there. And then all those channels would come down, the channels that I showed you going down the flank of the volcano. But I also just said that at least some of those channels were formed maybe by lava and then reoccupied by the meltwaters from a glacier that formed later on. Stuff like that happens on Earth. In Iceland, it happens all the time. Other parts are covered by glaciers too, maybe. All those channels that formed on the area that we still see either were fed by groundwater seeping, by glaciers, or by precipitation. According to current Mars climate models, which want it to be cold, remember, cold and icy Mars, weak early sun, glaciers are the most reasonable explanation. That doesn't mean there could not have been any precipitation in the form of rain. Probably only due to large impacts and very large volcanic eruptions that might have enabled transient rain events. After that, we get more eruptions, but now we form ash deposits. We see these ash deposits everywhere. That's one of the units I didn't show in detail, but we see units that's where dark, fine materials eroding out of the flanks, which is very likely ash deposits. And it covers the entire area. Not everywhere anymore, but we see indications that it once covered everything and that there's bits and pieces everywhere, randomly distributed. So a lot of ash probably came out of the youngest of those patera of this likely volcanic calderas, the last one to form. And then we have the picture today. continuous impact cratering, messing up our beautiful story, and covering parts of the area with ejecta blankets, and then continued wind erosion, removing bits and pieces of the earlier deposits. To wrap things up, we go back to this beautiful Mars Express image. So we think we know that one of the biggest calderas on Mars was probably sourced from the mantle. 60-kilometer deep stuff that came up. So let's land there. Where else to get that? That is extraordinary. It's a difficult place to land, though. It's very far south, very close to the poles. Light, there's not a lot of light there. It's cold. One of those days, maybe. We know that those wrinkle-rich plains, we derived the volume of those. We think we know how thick they are. We map their extent. Now, if they were formed by volcanic eruptions, lavas like building up those plains, volcanic eruptions always include gases. Like the main gas that comes out of the Hawaiian volcanoes is steam. There's a lot of steam coming out of there. There can be hydrogen coming out of them, methane, very, very climate active gases. Now, if you look at how much gas, how many volatiles are usually in volcanic eruptions on Earth, usually ballpark figures, then the amount implied by those wrinkle-rich plains that I showed you would imply 0.8 meters of GEL. Now that's global equivalence layer. You could cover the surface of Mars with 80 centimeters of water and or add almost 4 millibars of pure hydrogen to its atmosphere. And that would possibly increase the temperature over hundreds or thousands of years by tens of degrees, according to climate models. Now we see that this is one area, and this one area indicates that its activity probably changed the climate, at least in transient periods, quite significantly. And this is just one area. And then, of course, all the material transport. We wanted to know, where did all the stuff come from that ended up in this big basin, which appears bright here because there's a lot of bright dust in it. And it's also the origin of many of Mars's dust storms. They originate in this big basin. It's very important for Mars's weather. Anyways, all that stuff that sits in there, where did it come from? Well, a lot of it came from this area and this area, the South Pole and the area that is between Malioplanum, the area I mapped and looked at. And at least 500,000 cubic kilometers of material, possibly more, was transported down either by glaciers. It might have been lava itself as well, might have been ash, mud, winds, of course. So that's at least half of all the stuff that used to be in Hellas. Some of it got removed by wind already again. That all these dense valley network I showed you, which might have been fluvial, might have been volcanic, might have been both, going down the volcano flank down into the Hellas Basin. They're called Axios valleys. It's one of the densest valley networks on Mars. This is how dense it gets on Mars. On Earth, it gets even denser, okay, but for Mars, this is already a pretty dense valley network. And it might have been formed by low viscosity lava or water or both. We do not know. Most likely, though, is sequential. It might have been formed originally by lava and then reused by meltwater from a glacier that formed on top of this volcano, which is something that we see in a same and similar fashion in Iceland and many other areas on the planet. Also Alaska, for example. And then that very, very big channel, Maat Vallis, connects the South Pole with the biggest hole on Mars, Hellas Basin. So there's continuous material transport that must have occurred all the way from there to there, which is thousands of kilometers. That's putting the River Nile to shame. Although we don't know how long this thing was active, of course. Thank you for your attention. I'd be happy to take questions.
Are there any questions here in the church? I've got one question. The current mission on Mars, is it likely to provide any data or information that will enlighten some of the dilemmas you have in this area?
Potentially, yes. So particularly there are two types of data that might help. One is type of data that I mentioned before, spectral data, which is, it's also spectral observations are used in astronomy as well all the time, right? That's how we know what a distant galaxy is made out of, or a star. Now, we do the same thing with planetary surfaces. We look at the spectrum and we can determine the mineralogy of the surface. Now, if we look at those folded mountains in the big Patera, in that big volcanic caldera, as I said, if we get a dust-free, clear observation of those folded layers in there, that would indicate that they contain minerals that come from Mars mantle. There are minerals that we could see in that way that we could definitely associate with Mars mantle, like magnesium-rich olivine. You could see that if it wasn't that dusty. The surface is dusty, not the atmosphere too, but you can wait for a clear day. But the problem is the surface is dusty anyways. That would be almost a smoking gun. That would be very helpful. And maybe as we get more observations of that area, that because there haven't been many attempts yet to look at this specific spot with that instrument, that's an instrument of Mars Reconnaissance Orbiter, by the way. It's called CRISM, that could do that. So we need to try a bit more. Maybe we get lucky and see something there. But so far, we've only seen the dust, the ubiquitous dust. Another form of observation would be gravity. Now, gravity maps of Earth and the Moon exist. There are gravity maps on Mars where you map out the variations in the gravity field because it's not homogeneous, of course, and the subsurface determines anomalies in the gravity. So that could shed a lot of light on what status and those big volcanic features, those big calderas are in, if their magma chambers have been completely emptied, how deep the magma chambers are, like would be an independent piece of data that could inform these questions. We do have gravity maps of Mars, but right now there are too coarsely resolved. Their resolution is around 150 kilometers per pixel. Now, I did look at these and I was able to squeeze some important insights out of those in relation to the landforms I showed you. But in order to really look at the detail and get information about a lot of specific parameters of those potential volcanic calderas, as I said, the size and depth of the magma chamber, or if the magma chamber is still partially filled or completely empty, all these things, we need higher resolution gravity maps. That might be achieved with the current missions, but then you would have to make some alterations to their orbits, so that's very unlikely to happen. So we have to wait for a specific Mars gravity mapper. There has been such a mission not too long ago to the Moon. Its name was Grail, that produced high-resolution gravity maps of the Moon, and something like that for Mars would be very nice, for example.
Okay. Any other questions here in the church? I checked the chat and there wasn't any there. So if there's none, then we want to thank you for the great presentation. And we'll essentially carry on now with the rest of the club business, and you're off.
Thank you very much.
Thank you.
Thank you very much for having me.
Okay, while Bob's doing that, we have a few announcements. Next month, this is our last time we're going to meet here in the church for this spring. We're going to have our picnic in May at Beardsley Park. I'll be sending emails out and with the maps and everything for those who've never been there. And